We have Jesse and Ricardo here today. Thank you for coming here. They're presenting recent advancements of, or the, say, successor to Theano, Pytensor. Give it away.
Hello. Yeah, we have the links here if you want to follow the slides. The one that will perish, but it's easy to type, and the one that will survive. So we'll talk a bit about the library we spend a lot of time in, which is Pytensor. You probably didn't hear about it, but you might have heard, if you're old enough, about Theano. And Pytensor is a successor to it.
Spacebar.
What?
Spacebar.
Spacebar. Yeah, so just a bit about us. Jesse is doing a PhD in Paris, and I'm working, well, we're both working at Pytensor Labs, a consultancy. And we have some hints if you want to find out where we live right now. And importantly for this conference, we are both core developers of Pytensor and PyMC, which is built on top of Pytensor, and a couple more projects. So for today, just a reminder, what was Theano? It was, under the popular perspective, it was one of the first kind of popular deep learning libraries in Python. It precedes several of these, like JAX, Xarray didn't exist then. Pytorch, I think, might have existed at the same time. TensorFlow was inspired by Theano. And it died or disappeared kind of 10 years later. And we think that, on the one hand, it's true, it was a deep learning library, but it was quite more than that. It was mostly a kind of library to do meta computation or meta programming with computational goals. Had a lot of tools that are kind of unique, also made it a bit weird for users, but are quite powerful, and we think they are still useful today. Here I stole, or print screened some Reddit thread when they announced Theano was going to die. Someone that saw some of the potential there, they were sad that it was going to die because it was much more than just deep learning. It was, in his view, a complete symbolic math library that just happened to have convolutions and batch norms in it. And we do believe this is a good statement. So Pytensor kind of, we forked a library that forked Theano, so it lives under us. And today we would draw the picture a bit different. We would put Pytensor above these frameworks because it's more abstract, and in the end we can actually compile to all the backends in the end to compute, but we work at a higher level of abstraction. And we'll try to make today the case why this is useful for researchers and also people developing libraries. So for researchers, mostly if you're writing numerical computation, which most people here will be, you want to be sure that you are writing performant code. And something that's more unique in Python that you are able to explore variations of your problem space a bit programmatically, not just write a function, rewrite it a bit different, but maybe have the tool that allows you to explore it automatically. For developers, which we are more than researchers, I would say, it's a really good tool to develop some framework that's kind of flexible and can be developed in a way that might be more natural for, if you have a astrophysics audience or molecular biology, you can write a library that allows people to be expressive in, let's say, natural language, and then convert that to number crunching in the end. So the story why we're going to motivate Pytensor today is users want to write some numerical code for their case. It might be just a generic logistic regression with some cross-entropy loss. You as a developer, you want to do something on top of these, but Python is not really rich for meta-programming abilities. You would like to somehow have a representation that's more kind of boils down the computation that the user wants, and you can work on it. You can read it programmatically, obviously, and you can manipulate it for your use cases as a developer of a package. But if you just ask Python, what did I get from the user, you're going to get some, it's a function, not very useful. You can maybe get the doc strings if you are in an IPython and you could parse it by text. That's not going to scale well. You can try, Python has some tools. You can do bytecode parsing. Some libraries have chosen to trace, so you run user functions with dummy inputs and you just check what's happening inside the function. Pytensor and I guess Theano, when they started, it was decided not to go with much of this magic and just kind of found a compromise where you say, you can write code that looks almost like the one you want, but it's a bit different, and what you give us is already a nice representation to work on top of it. So the user the hardest thing is they have to specify kind of dummy inputs, what's going to be the inputs of the graph. Then they write mostly NumPy-looking code. But we as the developers or the package that then gets these objects, we now have what we want to work with. So we have just we have a graph of the computation the user is interested in that we can start working on. We don't need to go a few hoops to get that graph. So everything we get from the user is like lazy. There's no number crunching yet. It's just placeholder variables that are strictly typed. So we know loss is a scalar float 64. It's a tensor type variable. You could have sparse variables. You could have symbolic slices. Mostly you work with tensor variables, which would be the symbolic alternative to NumPy arrays. And then you can start working the graph. So variables can either be root variables that the user defined as you saw before, or they can come out of the application of other computations, of other operations. You get that through the owner of the variable. Then the owner can have an operation, in this case it's the sum, with axis equals none, so all the axes get reduced. And from the owner, which is the application node, you can also ask what are the inputs that go into this graph node and what are the outputs. The outputs is the thing we started, the sum, and the input would be the addition term that was there. And you can just keep going up the graph, always getting these dummy variables, knowing their type and kind of the computation that underlies them. And you get that representation that I just showed in the beginning, that if you are doing metaprogramming, it's nice to already start at this level of abstraction. And then once you have a graph, what can you do with it? We have some examples here. You can query it. You can ask, does this graph contain X? Does it contain Y? You can transform it for your purposes. You can obviously evaluate, and that's an important step. And usually you can do this in an iterative loop. Maybe you transform the graph a bit so you can query something about it, and then you transform it a bit more to answer different kinds of questions. And a big important thing is many of these tools exist in other computational frameworks, but they are usually not so pure Python. And Pytensor really sticks with Python to make it easy to work on this graph, manipulate it, and do all these kind of steps. So I'll just give you some quick examples. First basic thing is you can query what are the root inputs from my expression. It's just something you might need to. But you can do more interesting things. So in our application in Bayesian inference, a lot of times you have expressions like log of sigmoid of something. And there are many variations of this simple expression that you can do numerically more stable. And we just show a simple example how easy it is to kind of query if this succession of operations exists in our graph. So you could walk through the successors of a variable, and you can just ask, does my variable, my intermediate variable, come out of somewhere, or it's a root? So whether the owner is none or not. If it's not, does it come out of a log operation? And then, does this log have as input something that comes out of a sigmoid? Okay. And in our case, if you're running the notebook, it comes out that, there is a log. No, I cannot scroll. Doesn't matter.
Okay, yeah.
Yeah, we'll survive. Okay. Once you query a graph, you can start to transform. So as I mentioned, log sigmoid has some forms that are numerically more stable. And we just wanted to show that it's easy to just have a graph and modify a part of it, intermediate node. So we just iterate through our function that returns cases where there's a log sigmoid term. We get the x of that, and then we can do a graph replace. So we have the original expression the user gave us, and we just replace all the log sigmoid terms by minus soft plus of minus x, which is numerically equivalent, but more stable. And just to show that it works, now the graph has indeed the negative of the soft plus of the negative. We truncated it here. But you might not just want to rewrite equivalent graphs that are or equivalent computations. You might want to actually change the meaning of what the user gave you. So for instance, you could, for your purpose, want to add some randomness anywhere in the system, and it's equally easy to just say grab a node in the graph and replace it by it plus some, let's say, Gaussian noise. Or you could want to ablate part of the system. So how does the result changes if some part of the graph is turned off? Here's just a cute example where we multiply by 0. There are other tools to do that. And other transformations you can do with the graph, you can do autodiff. This is baked in, I didn't mention because it's kind of trivial these days, but it was it was necessary for deep learning framework, so it was there from the beginning. You want to do efficient vectorization, so transform a graph that works on a vector like a time series, and now you want work in parallel on multiple time series. You vectorize the graph. Bit quantization is another kind of graph manipulation / ablation that you might want to do. And then when you compile these, or when you transpile a graph to something that actually crunches numbers, you might want to specialize for different backends. So your final graph might look different if you're compiling to code or chunks or anything else. Numerical simplification, code elimination, anything you might want to do in your workflow. And finally, once you, at the end of the day, you need to be able to crunch the numbers. And the reason Pytensor went to the top in our graphical representation is that these days you can actually ask to, let's say, make your graph concrete into a backend. You can tell it, I want to evaluate it using JAX or Numba or C, and usually it's just a one keyword argument away. And we're just showing here it works. We have Pytorch, it's a bit more experimental. And the point is, we have such a simple abstract representation that's very trivial to execute different backends, especially with work that's being done to standardize how the APIs look across different libraries in the Python ecosystem. And yeah, that's where I would leave with this short example. I'll pass to Jesse, who will work out a more full example to give a flavor of Python.
Yeah, thank you. So my contribution to this is Ricardo kind of gave you the high-level overview of what is this package and why you'd want to do it. This is admittedly somewhat abstract, so we wanted to have more of an applied example. And we're going to take sales forecasting in kind of a time series environment as our example. And if that doesn't interest you, I don't blame you. But the idea here is to think about you're a developer of some package that has some purpose, and there's going to be domain-specific knowledge that's tied up in the types of things that you're trying to do. And so what Pytensor allows you to do in a very extensible way is to bake in some of that domain knowledge to provide more efficient computation to your users, and also to allow them to think in terms that they want to think in. Where we come from in the Bayesian language, or the Bayesian land, the most common example of this is log probabilities. Rather than writing down the log probability of your model, you'd rather think in generative terms and say, this is how my data occurs by some steps of random draws. And then Pytensor can automatically invert that process. Once you've defined your generative process, it can automatically say, given this generative process, what's the log probability of data that comes out of this? So the user is able to think in this natural space. So we're taking a simple example here of sales forecasting. The specific model we'll use is this Facebook profit type model. And again, this isn't super important. It's just to say that you have sales, which has these 3 time components in the front, and then it's a linear function of prices. And this beta coefficient should be negative, right? Like prices go up, sales go down. So our quote unquote package, the purpose is you're going to give it a time series of sales, you're going to give it a time series of prices. It's going to estimate the relationship between these two using this formula, and then also do some post-estimation analysis with the more advanced features of Pytensor. So this is how it looks. Like Ricardo said, we have an API that tries to follow NumPy very, very closely, with the exception of having to define these root variables, which, if you're used to working in SymPy, for example, this makes sense. You have to define an sp.symbol. For us, you have to define a pt.tensor to start your computation. Once you have those symbolic objects, then you're just going to write down these formulas exactly like NumPy. And then once you're sort of happy and you know what your output is going to be, you're going to call pytensor.function, which will actually do the transpilation into some number crunching language. By default, the backend is C, But now, as Ricardo said, we're adding more and more backends. You can ask for it to come out in Numba, you can ask for it to come out in JAX, you can ask for it to MLX is a new experimental one we have for Apple Silicon, and Pytorch. So, okay, and this is just what the data that I generated happens to look like. So we have some price time series that goes up and goes down. We think of like sales or whatever. And then you have an observed sales, which is affected by the price, but also has its own idiosyncratic dynamics. So in order to do this, we're just going to use stochastic gradient descent. And all I want to show in this slide here is how we can call pt.grad in this cell 39, passing the parameters. So it's a quite nice natural autodiff thing. You don't have this like differentiate with respect to which argnum of your traced function sort of API that JAX has, or having to declare that this is going to require gradients like Pytorch has. And that's all because we have the graph that we're working with underneath. You just have some graphical computation. You say, I want to transform this graph from a forward to a backward with respect to these variables, and you get back a new graph. So this parent grads is a list of graphs, and then we can pass that into our update function. And then we'll pass that into SGG optimization, which just does stochastic gradient descent, and I've highlighted the details there. And okay, it trains, you can believe me, and we get some predictions. Fine. Here, the purpose is not to be correct, it's just to show you something. Now, there's a few points, so a few powerful things we get out of doing it this way. The first is the reusing of intermediate results. So if you had just written a function in NumPy, like a NP, like a define make prediction, you would have all these intermediate steps inside. Like what's the seasonality component? What's the trend component? What's the residual of the computation? And these are all of interest to the analyst who's running this package. In Pytensor, though, each one of these chunks of computation is itself a subgraph, and you're at any time allowed to go back and reuse these pieces. So, for example, I could create some decomposition function that also takes time, price, the observed sales, and the parameters, but then I'm going to return 1, 2, 3, 4, 5, 6 computations, and that's all of the components of the final output. So just automatically, I get back the decomposed time series, and you can pick out, like, this is the cyclical component, this is the trend component, this is the price component. Pytensor is also smart enough to compare across these graphs, so it's not going to duplicate computation. So to the extent that what is in the intercept graph also exists inside of the residual graph, it's going to compute that once and then reuse it everywhere that it can. So it's doing automatic optimization, it's doing automatic memory management. It's really trying to give you back the smartest computation that it can without the user having to think about any of this. Okay, and then this is what you get, right? This is this profit model with these discrete change points. So then another powerful thing is that we can go in and we can just modify chunks of the computation without having to redefine the whole graph. So this occurs again in Bayes when you have this quote do operator, where you want to say, I want to rerun my analysis, but conditional on some piece of it taking some specific value. So the example here is like, let's say that the Grinch steals Christmas one year and the cyclical effect goes to like 10% of what it normally is. So without having to rebuild a whole new function, without having to generate new basis functions to compute this season or wherever the season comes from, I can just say, take the seasonal term from index 150 to 200 and then just change it to be 10% of what it used to be. And then recompile this function. And then automatically you get this update. And whatever data you pass in, this is completely irrelevant. It would symbolically have multiplied by 10% on that data. So if you change it, you'll still have the same effect, just with a different line. So another kind of the most powerful thing you can do is to really lean into this symbolic algebra side of Pytensor and start thinking about how you can manipulate the user's graph in order to give back some other graph of interest. And my example here is going to be profit maximization. So you have this pi t, which in economics is profit, and the profit is the quantity that you sell times the price you sell it at minus the quantity that you made times the cost that you bought it at. Fine. And then you can set up an optimization problem and look for this p star. So I want to choose my price now such that I maximize my profits. And this is analytically tractable for certain choices of qt. So remember that Qt here is a function of p. This was important in the beginning. We had that beta times price term in the model. And because it's linear, if you just work out the algebra, you'll get an expression for p star. So you have two options now. You could sit down and say, user, figure it out, push a pen, get this thing, and then compute it yourself. Or we could ask ourselves, could we take this profit graph that's derived from the model graph, could we somehow analyze the model graph and say, is this a linear model? And if it is, can we extract the graph for the optimum price just by analyzing what the user gave us in the first place? And that's kind of what we're going to try to do here. So the first thing I do is I write this find optimal p function, and we're just going to use a root finder. So like the really robust case that covers everything. No matter what you give me, I'll just use some Newton descent thing, and I'll find the zeros for this function, and that's going to be the optimum p. And it works. You get back something that looks like this. You make more than you used to. But you can do better, again, because we have this linear form. Okay, this is just showing that our profits went up. Great. Okay, so this is what if you actually push the pen and you get the math, you get this p star, and this is a well-known result in monopolistic competition, industrial economics, whatever. So the more interesting thing is we're going to do a sequence of rewrites on the graph. So way down at the bottom here in 64, I'm setting up the price. I'm taking the derivative of the price, and then I'm going to do a set of rewrites called canonicalization. And all canonicalization does, thank you, is that it says there's some standard form to put everything in, right? So expand terms, put change subtraction into negative addition, things like this. So we have a standard form to reason from. We can add more rewrites. So here I distribute multiplication over substitution. And Pytensor has a very powerful and extensible language to write these kinds of rewrites. And then we just march through the graph once we have these rewrites, and we say, can you find me this closed form solution? Is it linear, and can you give it to me? And if it does, it gives you back a closed form solution. It says, yes, the price is a function of these two variables, A and B. And then from that, we can just directly compute that the optimal price is minus A over B. And you get the same answers when you run the root finder. So you could imagine an API where you have a lot of these types of solutions baked into your package, and then the user gives you some model. You march through all of these different options, and you say, well, you gave me something. Do I know what it is? And if I do, I'll specialize my computation in order to give you something better than just doing a numerical optimization. So kind of just in conclusion, Theano was unique. It rode this line between a deep learning package and a symbolic algebra system. It kind of got to be known as a deep learning package, but our argument is that what made it really special and really powerful was the symbolic algebra part. And so we're trying to lean into that and try to find new applications for it, including these rewrites, these optimizations, these stabilizations, and then this ability to do transpilation. So another example of an extension. Now we're working with named dimensions in this sort of tensor package. So automatic broadcasting. You say that you have some tensor with a user and a choice, and you want to softmax over dimension 1. What is dimension 1? Who knows? But now you can use this sort of X-array syntax, and it'll automatically figure out which dimensions you're talking about. And then also automatically broadcast mismatched dimensions if you're in that situation. And we have a small ecosystem that's sort of growing up around Pytensor, mostly the PyMC and the related packages, but then there's a few others that are creeping up. And we're sort of here to let people know what this is, why it's useful, and hopefully grow that ecosystem up. So yeah, thank you very much.
Thank you both. Any questions?
A question from my side. So now with this whole array API thing, are there any plans to make this library play along with other arbitrary compliant plugins?
Well, yes, that would be great. We copy NumPy really, really closely. So actually we were talking during the lunch break that it shouldn't be too huge of a lift to get us there. in terms of API compliance. Do you have more thoughts?
So there's some trickiness where most of these libraries that are being adopting the framework, they are eager libraries, or they are not really symbolic or lazy in the way that we are. So some of the things we talk with them, some of the things are hard, but 99% of the way we want, and we actually want that. So I think it's time for people learning Python not have to learn the tiny chords of different frameworks. And we try to sit there on the top and say you can do every, we definitely should offer that. And yeah, something we are pursuing.
And another question which has not been very clear to me, what is the status of the GPU support? Because it seems like some things work, some I'm not so sure.
Yeah, so back in the day, Theano had its own GPU framework. That was hard for us to maintain, so we just cut it all. So we cut our code base by 90%. These days we lean on other libraries that offer GPU natively, so if you compile into JAX or Torch, you can just use GPU as you would use through those libraries. Numba would require us to kind of re-implement it ourselves, but we offloaded that to the more number crunching libraries, and we try to keep it just light and focus on this abstraction of the graph properties, and then let you get out of the way once you want to use your GPU or parallelize across your hundreds of CPUs, things like that.
So there's no OpenCL?
No, we don't write our own GPU kernels.
Okay.
Yeah.
If you have funding, we'll do it.
He will do it. I don't think we should. No, that's really very fast, and there's big money being thrown at that. I don't think it's where we can get a competitive edge.
Okay, then thank you.
Thank you.